Welcome back, Physics 30. So this is the photoelectric effect investigation that we'll be looking at, and you'll be using the online simulation, which we'll talk about in a second. So it's the photoelectric one. And basically the principle here is that a light that shines on a metallic surface, so the light contains some energy, and the energy that the light does serves two purposes. It has some of the energy distributed to dislodging an electron from the surface of the metal, and the remaining energy gives those electrons enough kinetic energy to move across this vacuum tube and hit the other side. So all the energy from the light source, part of it is used to dislodge the electron, or which is referred to as the threshold energy, and the remaining part goes as kinetic energy. But we need to do a couple of preamble things before delving deep into this little online simulation. Some of it is a review from physical science from last year. So let's take a look at a couple of things here. We'll take a look at, first of all, let's start off with the universal wave equation, V equals lambda F. So that, of course, is universal wave equation. And of course we have velocity is equal to wavelength in meters multiplied by the frequency. And if we're talking about light, we can use it, C is equal to lambda F. Okay, so we have the speed of light. If that's what we're measuring the speed of. And of course, that is 3.0 times 10 to the 8 meters per second. And of course, over here we have wavelength, which is in meters. And we have frequency, which of course is hertz, or seconds to the -1, or 1 over seconds. Okay, so we start off with that in terms of waves, what we're dealing with there. And in the last section we looked at using Planck's constant. The energy of a light wave is equal to h multiplied by f, where energy of the light, or of the photons, as we'll see, or photons, is measured in joules. Frequency, again, is Hz, hertz, or seconds to the -1. And h is Planck's constant, which we looked at earlier, 6.626 times 10 to the -34 joules seconds. Now up here, let's see here, so since C is equal to lambda F, or if I solve that for F, divide each side by lambda, I get that. So what I can do is I can take that and place that into here, and this equation all of a sudden becomes hc over lambda. All right, so that's another way. So we could figure out the energy of a photon by knowing the wavelength of it, but that wavelength has to be in meters. So quite often we have wavelengths in nanometers, of course. So what we may have to do is change that now. So when dealing with wavelength in nanometers, so we can easily convert from that from meters to nanometers and vice versa. So if we have it in meters in this section, we can convert it to nanometers. But since we do a lot of dealing with nanometers, and also looking at energy of single electrons, There's another unit of energy referred to as the electron volt, or EV. We can use the following, because in the little simulation we'll have to do that. So we can use this equation, which is E is equal to 1.240 times 10 to the 3 electron volts times nanometers over lambda. So it's very similar to this. It's basically converting H and C into this number here. So we could kind of think of it as a combo of Planck's constant and the speed of light. And of course here we have energy. The energy will be not in joules this time though. So energy of photons will be in electron volts. So if we're talking about energy of single electrons, of a few electrons, that's where this comes into play. And of course, scientific notation, we could simply say E equals 1240 over lambda, where of course lambda is in nanometers, and our answer will be so many electron volts. Okay, now an electron volt, let's maybe define what that is. So 1 electron volt, so that's the amount of kinetic energy gained by a single electron accelerating from rest through a potential difference or voltage of 1 volt. So when you have an electron moving through a potential difference of 1 volt, that's the amount of energy that it has in terms of kinetic energy. All right, so with that, now, so we'll have, so as I mentioned over here in this diagram right here, so electrons will go flying off and hit the other side, and as I mentioned, the energy of the photons, some of it is used up to dislodge an electron, and the rest of it is in terms of kinetic energy of the electron moving across the plate. So when the energy of the light photon or photons is used to emit electrons from a metal surface, dot, dot, dot. So we have the energy, which I'm going to refer to as the energy supplied by the photon or photons is equal to, now quite often we call this as Ke max plus WO. Or sometimes that WO uses the Greek symbol phi, which means the work function. So maybe you want to leave it as WO, so W stands for work. Work function or amount of energy required to dislodge an electron from the metal. And of course over here we have kinetic energy of electron once it has been dislodged. So again, so part of the energy of the photons in the light source are used to kick the electron off the metal, and then the remaining amount of energy that it has is the kinetic energy that it uses to go from one side of a plate to another. And of course we can solve for KE here. KE max. So if I subtract W, of course we have this. Okay? And of course the energy of the photon from E equals HF. So we can easily figure that. Or of course, as we saw on the previous page, quite often we're given the wavelengths directly. E equals hc over lambda. Or when using electron volts instead of joules, we have that other way we can figure out the energy of the photon, 1240 over lambda. And of course, lambda will be in nanometers. Okay, so that's what's coming up for that. So when we look at this, just going through this is kind of an investigation. So you basically look at all of the questions here. And in the next video, we'll open up this simulator and we'll take a look at how to use it so that hopefully we can look at all of this and figure it out. And there, I throw in the equation there too, the electron volt one. All right, so in the next video, we'll open up the simulator and you'll be able to see how it works. And we'll see you there.